Bismillahirrahmanirrahim. Let's start a new topic, which is Fourier analysis of continuous time signals and systems. So this Fourier analysis will consist of two transformations known as Fourier series and Fourier transform. So first we will study Fourier series and then Fourier transform. So we will study these two transformations separately, although it is discussed in this book alternatively, but we will study it separately. The Fourier series basically tells us the spectral density or spectral representation, that is also known as frequency domain representation of continuous time signals through some transformation. So let's see what is periodic signal. Firstly, we need to understand that Fourier series only exists for periodic signals. Fourier series जो है वो सिर्फ periodic signals की exist करती है, non periodic signals की Fourier series exist नहीं करती. So what is a periodic signal? Periodic signal is defined as x of t in which there is a positive non-zero value of t, for which x of t plus capital T equal to x of t. यानी उसमें कैपिटल T की शिफ्ट दें तो वापस हमें वही सिग्नल मिल जाए. तो दैट मीन्स दिस सिग्नल x of t is periodic for all t, right? So fundamental period t naught of x of t is the smallest positive value of t for which this equation is satisfied, and f naught is equal to 1 over t naught. You also know this relation very well. This is also known as fundamental frequency, and omega naught is equal to 2 pi f naught, which is also known as fundamental frequency but in radians, right? So one example of periodic signal is this cosine signal. This basically is a cosine signal cos omega naught t, which is having some phase shift. So this represents some phase shift in cosine signal, which is not really necessary to write. We can just ignore it for the time being and assume that there is no phase shift in cosine signal, and this phase shift is equal to 0. So x of t will become cos omega naught t. This is a periodic signal. Another example of periodic signal is this complex exponential signal, which is e raised to the power j omega naught t, right? Where omega naught is equal to 2 pi over 2 pi f naught, or f naught is equal to 1 over t naught. So 2 pi e over t naught, or 2 pi equal to 2 pi f naught equal to 2 pi over t naught equal to omega naught t. This is the simplest relations we have already known. So this is omega naught represents the fundamental angular frequency in this exponential signal. Okay. So x of t, which is a periodic signal, can be written in terms of Fourier series as this equation. Is this summation k equal to minus infinity to plus infinity, and c of k. C of k we will discuss in a minute what is c of k, and this is a periodic signal again, e raised to the power j k omega naught t. अब इस सिग्नल को, इस periodic signal को, ये हमें पता है ये periodic signal है. If we compare this periodic signal with this fundamental periodic signal which we studied before, we can easily observe that we have added a k constant here. So k constant, we have added a k constant here in this power. So now we can view it as omega naught is there, but omega naught is sampled at k intervals. So k equal to k की वैल्यू होगी k equal to 0, 1, 2, 3 up to infinity. Similarly, k equal to -1, -2, -3, -4, -5 up to -infinity. So summation, so collect all these harmonics, so we will get this summation k equal to -infinity to +infinity. And C of k is known as Fourier series coefficient, complex Fourier series coefficients. So how to determine C of k from this equation we will see in a minute, and we will see in examples as well. So x of t can be written as, in terms of Fourier series coefficients, as summation k equal to -infinity to +infinity C of k, which is Fourier series, complex Fourier series coefficients, and e raised to the power jk omega naught t, which is a periodic signal, complex periodic signal, and omega naught is equal to 2 pi over t naught, or is equal to 2 pi f naught, right? So this C of k, there are two observations from this formula. From this formula, there are a couple of observations that can be made. So one observation that can be made is that x of t is a periodic signal and x of t is continuous time, right? While we added a summation, not integration, so that means C of k and this periodic signal, which we have sampled at k omega naught, these two complex coefficients and complex exponential signals are discrete time signals. तो ये C of k भी discrete time है, यानी ये Fourier series coefficient जो है वो discrete time होंगे, and this periodic signal e raised to the power j k omega naught t is also a discrete time. We made it discrete time signal. So in the end, if we add all the harmonic components, these are called harmonic components, C1, 2, 3, 4, 5, 6, and C0, -1, -2, -3, -4 up to -infinity. So k equal to -infinity to +infinity, these are called all the harmonics of x of t, and we collect all the harmonics by summation. The summation goes from -infinity to +infinity. So now how to determine C of k? C of k can be determined using this formula, 1 over t naught, which is fundamental period. T naught is fundamental period, and integration is over the interval of t naught. So this is, since x of t is periodic signal, so we integrate it over one period, right? Because we cannot integrate the entire signal because x of t is periodic, right? If x of t is periodic, then we integrate it over one period, from 0 to t naught, or minus t naught over 2 to t naught over 2, and so on and so forth. And here e raised to the power minus jk omega naught t d of t. So here x of t is, the observation we can make from this equation is that x of t is a continuous signal, so that we have integrated it over one period, right? While C of k are discrete time, complex Fourier series coefficients, right? So this integral denotes the integral over any one period, which is, we will most probably take it as a fundamental period, right? 0 to t naught, or minus t naught over 2, or to t naught over 2, these are commonly used relations. So if we put k equal to 0 in this equation, so we can obtain C naught. So C naught is equal to 1 over t naught, and an integral over one period x of t and dt. This is a simple integration where k equal to 0. So if x of t is real, since c of um, c of k is complex conjugate signal, complex conjugate coefficient, so c of minus k would be equal to c of k conjugate. यानी उसका अगर नेगेटिव पार्ट अगर ये रियल सिग्नल है, उसका नेगेटिव पार्ट अगर नेगेटिव कॉन्जुगेट ले लें उसका, तो नेगेटिव पार्ट वो ऐसे ही होगा जैसे उसका नेगेटिव उसका पॉजिटिव पार्ट नेगेटिव करते हैं. ठीक है. So if x of t is real, then c minus k is equal to c of k conjugate. This is another observation from this equation. Trigonometric Fourier series, we will not study trigonometric Fourier series because we have already studied in mathematical course this trigonometric Fourier series. So we will study the next topic of convergence of Fourier series. So convergence of Fourier series, there are three conditions. These are called Dirichlet conditions. Without these conditions, Fourier series does not exist. So number one condition is that x of t is absolutely integrable over any period. That is, ये जो x of t dt, this should be less than infinity. That means the energy in this signal should be less than infinity, or this signal should be integrable and the value should not go to infinity, right? So this integration must exist for the Fourier series to exist. So in order to Fourier series exist, this integration should be, this signal should be integrable, right? Number two condition is x of t has finite number of maxima and minima within any finite interval of t. So that means x of t should have finite number of maxima and minima. So it should be like this. So this is, if this is one period, this is, let's say, one period, finite period. So there are finite number of minima and maxima. What is maxima? The point at which the signal reaches its peak value. This is called maxima. So there are 1, 2, 3, 4 maximas and 1, 2, 3, 4, 5, 6 minimas, right? So there are finite number of minimas and maximas in this finite duration. So this satisfies Dirichlet condition. But if we take this example, so this signal has infinite number of maxima and minima in this finite period. Right? So this signal has infinite number of minima and maxima in this finite duration. So this signal does not satisfy Dirichlet condition. This signal does not satisfy Dirichlet condition. Third point is x of t has a finite number of discontinuities within any finite interval of t, and each of these discontinuities is finite. So this means let's say so this signal has finite number of discontinuities. This is one discontinuity, second discontinuity, third discontinuity, and then enough. So there are three discontinuities in this signal. But if we take example of this signal, so in any finite period, let's say this is finite period, any finite period, this signal has infinite discontinuities, right? हम इनको काउंट नहीं कर सकते कितनी discontinuities हैं, इसकी infinite discontinuity है. So this signal does not satisfy that Dirichlet condition number 3, while this signal satisfies the Dirichlet condition number 3. Right? So these are Dirichlet conditions, and if these conditions are fulfilled, then we say that Fourier series converges. If not, then we say Fourier series does not converge. Power spectral density means the power that is in the signal. ये chapter 1 में भी आपने पढ़ा होगा that power in a signal can be calculated as P is equal to 1 over T naught integration over one period and x of t square dt. So in terms of Fourier series, the power in the signal itself resides in the power of the Fourier series coefficient, complex Fourier series coefficient. यानी अगर हमारे पास Fourier series coefficient given हो तो हम सिग्नल की पावर जो है वो हम इस फार्मूले से कैलकुलेट कर सकते हैं. दिस इज द फार्मूला फॉर कैलकुलेटिंग पावर स्पेक्ट्रल डेंसिटी ऑफ अ सिग्नल if C is Fourier complex Fourier series coefficients are given. This is known as Parseval's theorem or Parseval's identity, right? So this is an important relation as far as Fourier series is concerned. We will study Fourier transform next time. So let's do some examples of Fourier series. So first example is determine the complex exponential Fourier series representation of each of the following signals. The first signal is cos omega naught t. So cos omega naught t can be written as, this is a solution, cos omega naught t. Cos omega naught t can be written as, using the identity, cos omega naught can be written as 1 over 2 e raised to the power j omega naught t plus e raised to the power minus j omega naught t, right? So this can be separated and it can be compared with this equation x of t. So x of t is equal to k equal to minus infinity to plus infinity. C of k e raised to the power j k omega naught t, right? So if we compare this equation with this equation, we can see that here value of k is 1, here value of k is minus 1, right? Here value of k is 1, in this term the value of k is minus 1, right? And there are two harmonics that are being added in this equation. There are two harmonics. And similarly, this is the complex exponential periodic signal. And what is the amplitude? Amplitude is 1 by 2. So C1 is 1 by 2 and C minus 1 is 1 by 2 also. So C1 is equal to 1 by 2 and C minus 1 is equal to also 1 by 2. And all other CKs are 0 for k is not equal to 1. K mod, हमने k mod ले लिया इसका. All other, so this Fourier series coefficients exist for only k equal to minus 1 and k equal to 1, and all other Fourier series coefficients are 0, right? So this was very simple example. Just we have to apply the Euler's identity that we have studied so many times in this course. The second signal is x of t is equal to sine omega naught t. Similarly, using Euler's identity, the sine omega naught t can be written as 1 over 2j e raised to the power j omega naught t minus a e raised to the power minus j omega naught t. Then separating the terms and comparing it again with this signal, here k is equal to 1 and C1 is equal to 1 over 2j, and here k is equal to minus 1 and C of minus 1 is equal to minus 1 over 2j. So C1 is equal to 1 over 2j and C of minus 1 is equal to minus 1 over 2j. And Ck is equal to, all other Ck is equal to 0 for k is not equal to 1 or minus 1, right? Number 3, cos 2t plus pi by 4. So remember the periodic signal cos omega naught t plus phi. Here omega naught is equal to 2 and phase shift phi is equal to pi by 4, right? So similarly, again we can compare it with this equation. Cos 2t, that means cos omega naught t, omega naught is equal to 2 plus pi by 4 is phi. So compare it with this equation and we get values of, put values of omega naught here. This becomes e raised to the power j 2k t, because the value of omega naught here is equal to 2. Omega naught is equal to 2. Now applying Euler's identity again, this will become 1 over 2 e raised to the power j 2t plus pi by 4 plus e raised to the power minus j 2t plus pi by 4. Again separating the terms, this will, and comparing it with this equation, so here omega naught is equal to 2 and we can see that E is equal to J2T and here is equal to J2T with omega, where K is the necessary term. which is equal to 1, because if we compare, इसको अगर compare करें इस portion के साथ, so we get the value of k which is 1. k is equal to 1, because अगर 1 होगा तो तभी e raised to power j2t ये बनेगा. ठीक है. So here k is equal to 1 and here k is equal to minus 1. So that means we have Fourier series coefficient c1 and c minus 1, and amplitude of these signals are, Fourier series coefficients are 1 over 2 e raised to power j pi by 4 and 1 over 2 e raised to power minus j pi by 4. Again apply Euler's identity and find out the values of e raised to power j pi by 4. This will be equal to cos pi by 4 plus j sin pi by 4. So this will become 1 plus j over under root 2. This will become 1 minus j over under root 2. And all other ck is equal to 0 for k is not equal to minus 1 or 1. Right? So two more examples are left. You can do it yourself. These are solved examples. This is a solved example. Just we have to find the fundamental period. We have found out the fundamental period as in chapter 1, and after finding fundamental period, compare it with this general equation and then collect the individual terms after applying Euler's identity. Right? For cos 40 it is 1 over 2 e raised to power j40 plus e raised to power minus j40, and for sin 60 this will become this equation. Right? So after separating the terms, we get c2, c minus 2, c3 and c minus 3. Right? Because if we compare it with this equation, the value of k is equal to 3 here, 2 here, minus 2 here and minus 3 here. So just compare all the terms with this equation, with this general equation, and all other ck's are 0. Similarly, sin square t, the fundamental period of sin square t is pi by 4. We already know that from chapter 1, how to find out the fundamental period of signals. So just we need to apply Euler's identity and then taking the square. So 2j is, square of 2j is equal to 4 minus 4, and then this formula is a plus b whole square. We will obtain this equation after squaring this identity. Right? So here a constant terms is there, so that means c naught will be equal to 1 by 2, and k is equal to 1 here and k is equal to minus 1 here, comparing with this equation. So c is equal to 1 here, minus 1 by 4, c is equal to minus 1 here, minus 1 by 4, and c naught is equal to 1 over 2, and all other ck's are equal to 0. So similarly, you can do example here. This is simple example. This is a periodic signal, and we can take just one period of this signal from 0 to t naught, and it will become from 0 to t naught over 2, because this is integrable over 0 to t naught over 2. So apply this formula, apply the integration. You already know the integration, how to integrate, and then we will get this relation. So rest is very simple, just go through it and then you will understand the example. Similarly, this impulse train has been shifted, so the limits of integration would be from minus t naught over 4 to t naught over 4, right? From minus t naught over 4 to t naught over 4, and the rest of the process is same, right? So next time we will go through the Fourier transform. This concludes our discussion on Fourier series. Next time we will start Fourier transform.